computing, and hopefully we have gone from the different ways in which that can be solved to one of the many approaches, the big data approach, that is actually very convenient if we are the developers, because what big data has really managed is to split the actual functionality that we want to implement from all the message passing concerns, just by constraining in what functions we actually can express. As I was saying, MapReduce, this Hadoop model in 2008 was the start of all this movement really, but it also has some limitations, which has motivated the creation of many other distributed data-intensive processing systems. There are systems like Storm that we are not covering here at all, that they are, for instance, stream processing systems, which means that rather than having all my data already in my cluster, a stream processing system processes data as it is generated. So you can have a stream of events from maybe mobile sensors moving. You can have a network in which packets are coming in and out, and you want to detect anomalies. You might have camera streams, and you want to do some real-time analysis on those. Well, systems like Storm are designed for those type of applications, and they are not. They can do that. They cannot do the style of batch, large-scale processing that we have been covering with MapReduce. In a very similar style to MapReduce, though, there is Apache Spark, which is the system that we are going to be briefly introducing now. And to again give a bit of story, Spark has something unique actually when you compare it to MapReduce and to other systems like Storm that was created by a company that was quickly purchased by Twitter. In the case of Spark, Spark is actually an academic project. It was created in the University of Berkeley by the extremely successful AMP lab, and of course it originated in 2012 with a paper that got the Best Paper Award in the Best Distributed Systems Conference. But one thing that kind of distinguishes that group is that they not only do research, but they are really strong engineers, and they released an implementation of that system that was working really well, and they created a startup called Databricks that is the one that has been driving the development of this system for 4 years. But it's become really popular these days. It is the most active Apache project over the last 2 days, and actually it has grown really fast. I would say that maybe it has grown a bit too fast, because those systems are really complicated on the back end. There are many moving pieces that they need to be automatically coordinated and put together, and the strategy that they followed was to try to do everything, basically. Try to be the system that can solve any type of big data problem. And when you use Apache Spark, today I'm going to introduce the basic elements, but on top of those elements, you can use it as a large-scale database, running queries in a SQL language. You can also use it for graph processing in particular. We will be seeing how that works tomorrow. It also comes with actually a streaming solution. What I was telling you of Storm, of this stream of events, you could also implement systems like that on Spark, although I really don't recommend it. I've had some students using it, and it's really an unstable part, and it doesn't really fit with the rest of the system. And it also comes with lots of convenience machine learning functions. There is a separate project in which they have implemented not state-of-the-art deep learning techniques, but many of the standard classification and regression methods, you have them already implemented under Spark. So it is a platform that actually offers in theory a lot of functionality to you, especially when you compare it with how bare bones MapReduce was. But if I have to explain you what is really Spark, the main concept, the main idea of how Spark works is that it is a data flow programming model. And in a data flow programming model, what you are basically defining is a flow of operations. So I start here from some data, I transform this data in some way, I get this new data, then I create this third part of data, maybe I want to implement a loop to keep running this, and at some point I will get the result that I want to achieve. So when you are using Spark, rather than having to be restricted to a map and a reduce function, you can basically define whichever data flow you want. And in that sense, it does look more similar to how we write programs in a structured language. Because we are saying, first we do this, then we do that. You can define a loop, a while loop, and implement it as in any other language, and this is the final step. So they have done a really good job in having something flexible and something that looks more intuitive than what we are doing with MapReduce. And everything in those actual data flows that we have here is based on those intermediate data structures that we have here. Whenever we define a program in Spark, everything that we are doing is to basically transform one distributed collection, one very large set of elements, into another one, another one, another one, until we finally get the result. Which is kind of what we were doing, if you remember, in the previous hour with MapReduce. We had the initial data set, we mapped it into an intermediate set of key value elements, and then we applied another function and we generated the result. Basically here the difference is that we can have as many intermediate functions as we want, and as many intermediate collections as we want. And those collections are going to be the first order element of our system. We are no longer focused on what's inside the functions, inside the map and the reduce. We will be seeing the intermediate lists that we are creating on the way. And in addition to this convenient programming model, that's most of what I will be trying to cover in this hour, Spark did manage to, as we say often in research, to stand in the shoulders of giants. It does recycle all the attractive properties of MapReduce. It kind of abstract to all the dirty details of parallelism, message passing. It is fault tolerant, which is also the case for MapReduce. So if you are running a task of 100 nodes and one of them fails, the framework automatically tries to reschedule it on a different machine and make everything complete. It is again very scalable, so we can use it with massive datasets as long as we keep adding more and more machines to our system. And I was saying, one difference between Spark and MapReduce is that here in the way we express programs, the focus is put on the data, not on the functions. And when we define a data flow, it is going to be a set of transformations between distributed collections, that they are called RDDs in the terminology of Spark, which means that if I have this flow, this is going to be my first RDD. By doing something, I will create my second RDD, my third RDD, until I finally compute some result. So everything I am doing inside a Spark job, inside a Spark cluster, is some type of transformation, some type of computation on a distributed collection. And again, I don't have to know anything about parallelism when I am using one of those frameworks. So where will all of those collections live? Well, they are going to be living in RAM, in the RAM memory of the machines of my cluster. But I won't be aware of which machines are holding each one of the parts of that element. I will only say, this needs to be converted into this other element by applying this function, and then I will apply this other function to obtaining my results. And where those RDDs are living in the cluster, that will be part of Spark. That won't be my responsibility. And well, those RDDs, they have a lot of flavor from, again, functional programming languages. Because among other things, Spark is implemented in Scala, which is a functional programming language. And then you will see that in the syntax, we are kind of going back to this map and reduce slide that I showed you before. So we say, this collection is going to be mapped with this function. This collection is going to be reduced with this function. But another thing I didn't mention of functional languages is that the elements that we have are actually immutable. And this is something that is very strange if you have only seen standard procedural languages like Java, Python, or even something like MATLAB, in which you have variables. In a functional language, all my variables are immutable, they are final. Which means that if I start here with one RDD, the way in which I can move forward here is by creating new different RDDs to the one I had. So I am always going to be doing the same thing. Starting from one RDD, I can transform it on a new one. And again, if I take this new RDD, another transformation will create the next one and the next one until I have the results that I want. And well, in addition to that, how those RDDs, as I was mentioning, they exist in memory of my cluster. So in the case of the Moonshot cluster that we have downstairs, we have 500 gigabytes of RAM among all the machines there. Well, that is the shared pool of resources that we are going to have to share this afternoon. And in that, keep in mind, if things are a bit slow, that well, we have tried to downsize all the datasets so that you can actually use it in a shared learning environment like this one. But when you are using it for some specific use cases, you would expect to have access to the whole resources of the cluster. But all those elements will be loaded in memory, but they need to come from somewhere. You cannot just create 5 terabytes of data out of thin air. And what is usually the case is that then we do create those RDDs by reading data from a persistent storage source. In our case, and in many cases, we can reuse the same distributed file system that Google proposed for the Hadoop system. So that when we start our Spark flow, first we read from a distributed file system, and we create our first RDD, and from that point onwards we transform it until we get what we want. So that's the main idea. What we are going to be doing with those RDDs, we are going to be running 2 types of operations. The most common one is going to be a transformation, which takes one RDD and transforms it into a new one. So that I have this list of elements, I apply a function, and I have a new list of elements. And both this list and this list, they are existing only in my cluster. What is the problem of those elements existing purely in my cluster? That I don't know where they are, and I cannot actually read what values they have, because they are in the cluster. They are not in my machine. Because of that, there is a second type of operations that we can invoke in Spark that are called actions. And the goal of an action is to take an RDD that is in the cluster and basically retrieve from some value from it. Possibly some summary of that, possibly save it to a distributed file system so that I can read those results back, because I cannot read what's going on with those RDDs. I can say, okay, whatever I have here, I'm going to transform it into another thing. And this, I will transform it again. But the moment I want to retrieve results, I have to actually invoke an action. Okay? Let's then see one example, and the same word count example that I was mentioning before, to illustrate how then this looks like when we are actually using Spark. We have then the input is a set of words, a set of textual elements, and I want to count how many times each word appears here. This is stored in HDFS. I want the results to again be output to HDFS, and I need to write a Spark program. How would that program look like? Well, we can solve it with something like what you can see here, which might look like we have lots of different boxes, but if we start looking at the parts that we have here, first you can see that I have lines, words, and counts. 3 different boxes. What do these boxes represent? Those are 3 different RDDs, 3 different distributed lists that I am generating in my program. So the idea is, initially I have a data set of text. From that data set, I first create a collection of lines. Each one of the lines of my text will be one element from this list. Then something happens and I will transform my lines into words, so that rather than each one of the lines will become 15, 20 different words. This is going to be a second list with many more elements than the initial one. What else do I need to do in order to finish this count? Well, basically I need to group together all the repeated elements here and count how many times that element appears. So I need to transform again this list of elements into this other list of elements. And once this RDD already has the results, I will need to save it again to my persistent file system, because I cannot read the values for any of those elements. Unless I invoke an action, it is as if those actual RDDs didn't exist, because nobody can get access to those. So when you see a flow, the main intermediate steps are those RDDs that I am going to be creating and that will be composing the data flow. How do I obtain each one of those RDDs? I do that by invoking a set of transformations. And basically, what those transformations do is the equivalent of the map and reduce functions that we had when we were showing MapReduce jobs. The difference here is that rather than having only 2 functions and that they are always implemented in the same order, Spark does go with a much more ample list of transformations that we can implement. At the end of the day, all of them are equivalent to map, the grouping that takes place in the middle, and the reduce, but they have basically found different, more specialized versions of them so that all of them can fit into a single line. And if we want to see all of this together into an actual Spark program, this is how we can use 4 lines of text to count all the words that we have in a dataset. We start with an input path and we use a special method to create that into a first RDD. a first distributed collection that is going to have lines of text. How do we move forward? By transforming that initial collection. We are going to take these lines, and basically for each one of the lines we are going to split it into words, and we are going to put all those words together as elements of a new list. And then we move from a collection of lines to a collection of words. Then we need to take the full list of words and we need to actually group them together by how many times each one of those words appears. And these functions that you can see here basically do that task. We will get a little bit more into the syntax later. Once we have the results, again, this is an RDD. I don't have access to that. So in order to make sure that the result is there, I am going to save it back to the distributed file system. Okay. This is a relatively simple case because I am basically redoing one of the programs that could be done in MapReduce, but definitely everything that I could do in MapReduce I can actually do here. And the thing is that if you see here the source code that I have, this is basically a Scala program that I am executing line by line, and I have no restrictions in what operations do I want to write here. Whenever I want to trigger something on the cluster, the only thing that restricts me is that there is a limited set of transformations that I can invoke. But as long as I keep using those methods, I will be able to process the data anytime I can. Okay? So that's the general idea. I have here two slides with a very brief note on Scala, because I know only one of you is kind of familiar with it. You will see this later in the afternoon sessions, so don't worry much about the syntax. The main thing that you are going to be seeing is that whenever we define one of those transformations, this is an example of a map, what we are going to do is to take, in the case of a map, each one of the elements of my RDD, and I am going to apply the same function to each one of those elements. And in order to define the function, input parameters output, with the transformation that we do, we have to use some syntax. In this case, the syntax of Scala. Scala has 5 different ways of defining those functions, and some of them are more verbose, some of them are really short. For all these slides and in the labs, I have tried to be consistent, and this is the way in which I am expressing in one of the functions that you will see. We express it as a single set. On the left side of the function declaration, these are the parameters that I am using. So this is a function with one input parameter, x. And the output is whatever result I have here. In this case, if the output is x, the output is going to be x plus 2. So if I map a time series and I apply this function, I am going to shift each one of those values 1 up, 2 up. You will see that used over and over our examples. What can I do then with those RDDs? What type of operations are available to us? Well, actually, a lot of them in theory, although fortunately they are not that different from each other. So once you figure out some of the main operations, you will see that many are just slight variations from them. We have transformations. Again, those take an RDD and create a new RDD from it. And they basically do the 3 types of parallel operations that take place in a MapReduce job. Many of them are equivalent to a MapReduce map, although we have quite a few maps. There is map, filter is another type of map, we will see it soon, flat map is another type of map. And we have other type of operations that implement this group by idea, which basically allows us to take a list of elements and group them together by some common key. There are some join operations similar to what we can do in databases, so that we can combine two different data sets and get the matching elements from those RDDs, quite a few transformations. The actions are much more simple on the other hand, because the only point of an action, again, is to get the final result, so that we can actually save it somewhere. And we can either save it to some persistent storage, or otherwise, if the result we want to get, we just want to figure out some simple statistical property of my data, maybe it also makes sense to recover that and to retrieve that with an action. For instance, if I invoke count, what Spark is going to give me back is what is the size, what is the length of the RDD that I am invoking count on. Or I could invoke, there is a take method, for instance, that we don't have here, that will give me a random sample from this RDD so that I can see how my elements look like. So if I am exploring data, I am kind of figuring out what is there and I want to keep interacting with the remote RDDs, actions can be very useful for that. But really the core of operations are always done through transformations. Okay. A few more notes, because all of our examples are actually with Scala. And well, yesterday most of you told me that you were familiar with Java. So for all of you who are at least familiar with that, Scala is a language with very similar syntax to Java. It is actually compatible with it. Both of them are compiled to the same bytecode. And you can use in Scala any Java library and vice versa. There are three main changes or extensions to Java that you will see heavily featured in all of our Spark programs. One you have already seen, and is that we are going to be defining functions, which in Java 8 we can actually finally do that with closures, but Scala did bring that a few years ago to the Java virtual machine. The kind of secondary thing, but which makes the code look cleaner, is that in Scala we don't need to explicitly say what is the type of each one of my variables. The Scala compiler is quite smart in figuring out whether something is an integer, a string, a collection of elements. Because of that, in all the examples you are going to see that we just declare the variables as val elements, which are basically untyped. You can specify types, but it is not necessary, although you will get sometimes some errors because you are using elements that they do not have the time you would want. But this allows the code to look more similar to what you would be doing in Python or in other dynamically typed languages, because you do not need to specify that. And the third thing, which is quite relevant, is that in Scala we can define tuples. A tuple is basically a sequence of elements. 2 elements, 3 elements, as many as we want. And in particular, we are going to be using a lot tuples of 2 elements, basically a key and a value. How do we express that in Scala? Well, we basically say parentheses, first element, comma, second parenthesis, and we close that. And just by doing that, we can actually create a tuple of a key and a value. If we have a tuple, how can then we access the first element or the second element? We can do that. Okay, I don't have the example here, so you can say that a tuple of elements can be something like the word comma 1 that I was saying before. So this could be a tuple in Scala. if I want to access the first element here, the key here, I can do that by saying tuple._1. _1 refers to the first element. Whereas if I want to access the second element, I would say _2, and that would actually go here. We are not really using here today for the lecture, but you will find this later in the actual lab exercises. So just so that you are not surprised, when you see this _1 and _2, we are actually accessing each one of the elements that you see here inside your tuples of elements. Okay. All right, so we've actually gone through kind of the base idea of how we are going to be defining programs. A program is going to be a collection of transformations so that we keep creating one RDD after another. And the final results will be obtained by triggering an action on the final point of our program. But we have not said anything on how that actually takes place in a cluster, because this is another big data system. And in this case, and this is slightly different to MapReduce, and also what makes it more flexible, when we are running a Spark program, we are actually running kind of two elements in parallel. We are always running one driver, which is the client that is controlling the execution of all those steps, and then we will have the cluster where the RDD operations take place. So the driver is kind of the representative of the client, of the user of the cluster. And this can be a bit tricky. We will see some examples later. In the driver, we can actually run any Scala program. We can actually have variables in our driver. We can hold some elements. The tricky thing is that at the same time, we are going to have our local variables that belong to the driver, that belong to that user, and we are going to have RDDs. All of my RDDs are going to be not in the driver, but in the cluster. But at the same time, some of my variables will also be local to it. And if we are not careful by looking at the code and looking at what's going on, it might be the case that we assume that both of those elements are actually equivalent. But we will actually see in some examples in a few minutes how we actually will need to combine both parts to actually implement some more interesting programs. So let's try to view at the cluster and see what happens in one example, like the word count that we saw before. We start our program flow and we say lines equals text file from that actual folder. What happens in our cluster when we run this? Well, I have my driver program. This could be a machine inside the ITL where you are actually running all those commands, and the rest of machines are my cluster. First important thing, the actual path, the actual URL for the file that I want to load is actually resolved to not only one, but a set of machines of the cluster where that information is stored. And different blocks of that data set will be automatically distributed in different machines. So when I want to load that element into an RDD, we will actually create this RDD, and what it will happen is that each one of those machines will create on its term one different split of this distributed collection. So the lines RDD that I am defining, I am running the instruction here, but the information will actually be stored in those three machines of my cluster. So it can be a bit tricky to keep track of that when you are actually running your program, and then you will wonder, why cannot I read this value? Well, because you control lines from there, but lines is actually in other machines of your cluster. What happens when you write a transformation? This transformation takes lines, and from lines creates a new RDD with the words, the individual set of words that compose your data set. So we are splitting lines into words. Well, when this is executed, again, the instruction is read here, but it will be applied in the cluster. And from each one of those lines RDDs, a new RDD will be created, being again distributed across the cluster. So whatever we do in the driver, if it's an operation with an RDD, it will take place in the remote machines of my cluster, not here. Okay? So we have a driver program. Let's think that this is our ITL machine we will use this afternoon. We have a set of, in the same way as MapReduce, a set of blocks, components of Spark that we do not see, but they are making sure that my program is actually executed for all the data in a parallel way. So those elements will be then part of my cluster, and what's going to happen? I'm going to be starting my program by creating some RDD. And when I create some RDD, the RDD will actually exist here. It will exist on different nodes of my cluster. Whenever I run a transformation, the instruction is read here, but it will actually be executed on this other side, on the cluster. And new RDDs will be created from that. And finally, only when I run an action, I will be able to either get data back to the driver program, or possibly to save data back to the distributed file system that we have been using for persisting results. So what can you do and what is the effect of each one of those actions is quite important for you to see, because otherwise you might do things like invoking there is an action, so this takes something from the cluster and sends it back to the driver, and we have a very dangerous action that is called collect. What collect does is it takes your RDD and it copies it back to the driver. All of it. Well, if my RDD occupies 2 terabytes of data and is distributed among 100 machines, I will crash my driver program if I try to collect it. But it could be the case that when transforming multiple times my data set, I have some final results which is small enough so that I can actually get those results back. But figuring out whether we are transforming or we are running actions is quite important so that we don't actually kill our program. Okay. So what can we do then once we have created some RDDs? Just to give you 2 examples, these are really 2 variations of the map style of operation. When we have a map, we have an initial line of elements, initial list of elements, and we are going to apply the same function to each one of those elements. And then, depending on how many of those results will compose the new RDD, we basically have different flavors of our transformation. The most straightforward one is the base map. We create a new RDD that has the same number of elements of the initial list. For instance, you can see here some example in which we are processing tweets in general. We have a data set in which my initial RDD has a list of messages. Each one of those messages is one whole tweet. And what I am going to do is to parse the tweet and only get one specific field from it. because I don't care about the rest. I don't care about possibly latitude and longitude information. I don't care about many other JSON fields that are not important to me. If I don't care about that, for each one of those messages, I split it, separating it with commas, and I only get the fourth element here. And that I am going to get as a new element, as a new RDD. So map, one input element, one output element. Both collections have the same size. Another very common one is the filter RDD. Again, we apply the same function to each one of those elements, but what happens with a filter is that we will select a subset of the initial list of elements. So in the new RDD that we are creating, the elements of this grave RDD will be the original elements of logs that actually match this condition, this check that we have here. So here I have a set of logs, a set of messages from my server, and if my message starts with the text grave, so it is a grave exception in my system, I will keep it here. Otherwise, it will be discarded from grave. So you can see here we create new elements, but it's still a one-to-one mapping. Here we subselect, but we do not modify them. And if we want to filter and then subselect, you can chain, you can combine as many of those transformations as you need. But really both of them, in essence, they are a map style operation. For each element from the input side, we do something independently. This is another different example, the flat map that you saw before. Flat map is the same as a map, but for every input element, we can get more than one output element. And an example of that is actually splitting lines into words. As one line can have 12, 15 different words, we cannot map it one-to-one. We need to do a flat map. And then the result that we have here is actually a list of elements that it will be spread out and it will be collected in a larger RDD than the initial one. So all of those three are examples of I process each element of my dataset independently, and then depending on the flavor of method that I use, they are slightly different. One-to-one with transformation, one to maybe one or no one, and no modification here, and one to many in general. And those are very restrictive, as you can say. They are very specific in what you change. So what it happens in many places is that you need to actually chain multiple of those together to really have the data in the actual shape or style that you want. Okay? But once you get used to the syntax, they are relatively straightforward. Okay, sets are not that interesting. Actions. Again, we have mentioned those are the way of retrieving information from any of your RDDs back to either your program or to the distributed file system. And we will see a few of them later in the lab. So just, again, beware that they are risky, especially some of those like this collect. So only use them when you are sure that your driver can actually handle that amount of information. I've been speaking of map and quite a few map operations. The second kind of main type of parallel computations that we can run with Spark is reduce operations. And those reduces are more constrained, again, kind of more straightforward than what we had in MapReduce. Here, if I say reduce, I mean I take one list of elements and I only get one value out of that list. I am always getting one single result from that. So if I am implementing some type of sum function for some type of formula, I can reduce all those partial results, and I can reduce with a sum function so that all of them will be compiled into a single value. Here the syntax for the function is slightly different, because in order to reduce something we need to again implement a binary operator. For one variable a and one variable b, what we return is actually a plus b, but it is actually very similar to what you were seeing before. Okay, I have not spoken too much about that, but I think we have kind of seen what's going on. Whenever we create an RDD, whenever we actually create one of those distributed collections, we actually don't know where they are, but they are in general going to be distributed across multiple machines. They are going to be spread across our system, and as often with those type of elements, we do not need to control or to actually customize how spread, how partitioned my data is. By default, Spark decides how many slices each one of my RDDs is going to have, although if at some point some of you want to actually tune performance of your programs, it is possible to actually resize them and repartition so that this structure is split over 5 nodes, 10 nodes, or whichever nodes is actually made sense for the computation. So in general, with this type of framework, it tries to do its best if you don't specify anything, but it might be advantageous to be aware of the size of your data set, the performance implications, so that you can tune how the data is actually distributed, so that it actually parallelizes better, or you reduce the amount of computation that you have. And again, we are not really seeing what is taking place, but whenever we run a Spark job, we are actually doing lots of stuff in our cluster. For us, it might look like a simple 4 or 5 line program, but each one of our transformations, each one of our operations, in general is going to trigger some kind of distributed computation plus communication in the cluster. And here, not all the transformations are the same. We have this map operation that I was mentioning before, and map, filter, and flat map, all of those are very efficient operations because basically they are embarrassingly parallel. There is no need to synchronize to send any communication in order to compute them. For each input element, we get something out. And because of that, those tend to be very efficient operations. But there are other operations like the group by or the join. The group by, we are going to mention it quickly now, that they need to take a set of elements and basically group together all the elements with the same key, which is basically what MapReduce was doing for us between the map and the reduce. This operation is fundamental in almost every type of computation that we do at some point, because there needs to be some coordination, some synchronization, but this is very costly in general, because it is going to trigger lots of network communication across the system. And then, even if for us everything that we do looks kind of the same, if we just look at the Spark program, if you actually understand what's going on, what are the implications behind each one of those operations, you hopefully will be able to avoid doing things that make the cluster unhappy or just crash with not an informative error message. And in that, You will maybe see it later, but that is one of the downsides of Spark. It is a system that initially looks really welcoming, easy to use, everything seems straightforward, until something goes wrong. If something goes wrong, Spark won't give you any hint of why it crashed. It will just break, and as your computation is taking place in nodes far away in a cluster, it can be very difficult to actually debug what failed. So taking a step back and actually understanding how all those things go together, it can be actually very, very important. Okay, yes, I had a slide here about tuples that I mentioned before. So sequences of elements, we can actually create them just like this. Here we take one input element and we get a tuple of that element and a value of 1, just like that. And once we have created it, we can access those with those dot underscore 1, 2, 3 notation. Why are tuples that important? Tuples are really important in Spark because they are the way in which we can do all the more interesting transformations. In particular, there are two transformations that they are actually very, very useful here. One of them is the join operation, and any of you who is remotely familiar with a database will be very familiar with what a join is. I have one table, another table, and I want to obtain all the records matching this common field in those tables and pulling those results together. In Spark, I will want to do the same thing for several RDDs. Maybe I have one RDD with a time series in which I have for each one of the channels of my TV system, Twitch, that you will see in the lab, how many users were actually viewing that channel. And maybe I have another data set in which I have for each one of the channels which users are actually subscribed to that channel. Well, for some computation I might need to get subscriber data and popularity data. How to do that in Spark? With the join transformation. You join, and basically you join two different RDDs as long as both of them have 2 or more fields, and it basically matches elements with the same key and puts together the actual values from one and the other. That's one main example of a communications heavy but important operation. The other important operation is what is in general known as group by key operations, in which I have a data set, and in that data set I want to put together all of the values that actually have the same key. Like in the word count example I was mentioning before, in some kind of formulas in which I want to gather all the values that actually have the same index, I will do that with a group by key operation. Group by key is kind of a high level command that simply for each one of the keys collects the list of values that go with that key. If I know what I want to do with those results, I will use this other operation, this reduce by key operation, that takes the whole list of elements and again reduces them into 1. So if after seeing all those things, which are a lot, we go back to this initial program that I showed you some time ago, here you actually have in those mid to lines examples of most of those transformations. So if again I go back to this view, I have my set of lines, I want to get a set of words from those, and from those words I want to get the count of how many times each word appears here. How to do that? Well, the first step is very straightforward. I take the set of lines and I'm going to do a flat map. flat because each line has more than one word. I take the line and I basically split it looking for spaces, so that if the line was big data is going to blah blah blah, I will get big data is going each one of those elements as an individual element of my list. And now comes the kind of more involved transformation. How can I go from this list of elements into these final counts? And in order to do so, I actually need to go through two steps. First, I need to convert my list into a list of tuples, because we need tuples if we want to group elements together. And that's what I am doing here, or here if you want to see the text. For each one of the words I have, I am going to generate a tuple, keyword value 1. So this one means that if I go back here to this initial list of words, what I am going to map is a new RDD that it will be big, 1, data, 1, is, 1, and so on for each one of the elements I have here. So first I transform this into a set of words. What can I do with this now? Well, now I have keys and values. I can apply one of those group by elements, and in particular I can directly apply this reduce by key transformation, which for each group of values that belong to the same key, it is going to implement this reduce function, which is the sum function. It takes two elements, it gets one back. So that big data blah blah blah, big 1, data 1 is 1 going 1. What happens next? We take big 1, well, we don't have more. Here, for instance, is 1, another is 1. When we group those values, I will have is values 1, 1. And I will apply my sum function, my reduce function, to both partial counts. 1 plus 1 equals 2. When we apply that to the whole data set, this is going to be what I obtain. For each one of the words in my system, one single result that in this case contains the whole count of elements. And in general, it's going to be really difficult to implement any algorithm without going to those group by, reduce by key operations, because this is the part in which you can actually communicate, mix your data, and implement any function that is not trivial. Okay. Any question now that you've seen the code? Yep.
You mentioned earlier that there was a count action. Could that have been used instead of reduce by key?
No, because what count will give you is how many elements you have here. So you have 50 billion different words. But what we want to get is for each one of the words, what's the... And one confusing thing is that there is also a reduce action. And what the reduce action would do is take this whole list of elements and send back one result from those.
Does reduce function make sense only after a map, or only after calling a map?
It doesn't have to. In practice, what is usually the case with Spark is that you need to start with filter, map, flat map, because your data, you are loading it from somewhere, and you basically need to format it in the right way to be processed. And because of that, it's common to first have map elements before you reduce it.
And how can the reduce function know the key, reduce by key?
Because reduce by key, it actually does two things. First, it groups all the intermediate values by key, and then it applies the reduce function to the values belonging to each key.
So it has to be called on a collection of
Yes.
two-dimensional tuples. Okay.
Exactly. So both group by key and reduce by key need the RDD to be a tuple, a list of tuples. Okay. Okay. We are already at 12:30. Well, I still have a few things to mention, but I think it might be best if we drop it here, because I guess it's been a bit too much information. So what do we still have to mention that I will go quickly over that? Well, there is one kind of important concept that you are going to see in the lab, so then I think it's worth that at least I mentioned that. And that concept is that Spark is relatively smart because it's a lazy execution language, which means that it will wait until the very last minute until it actually executes your flow. You can define read from text as a text file, map, filter, reduce by key, but you will see this afternoon that Spark will not start working until it absolutely has to. And the moment in which it has to is when you are actually invoking an action, because actions are which allow us to get back results from all of those in-memory elements. So unless you run an action, the system is not going to start running. And that can be very convenient to Spark. The other bit that is quite important for how to operate Spark, that's why I wanted to finish here, is that Spark is lazy, and basically Spark runs all those operations from the beginning to the end. And unless we do anything, once Spark finishes this flow, all those intermediate RDDs are dropped, they are discarded. So if we run twice the same data flow, each one of those operations will be triggered again. And that can be a problem if we want to actually reuse some of those values, because we can have kind of an interactive interaction with RDD to explore some of those values. And in order to do that, there is a persist or cache operation that tells Spark, okay, you are not going to discard this RDD. So the first time this is invoked, this will be kept in memory, and I will be reusing it again and again. So that we can actually do something like what you see here. I have my driver, my workers, last slide, I promise. And I am first loading the actual information from the distributed file system. I create my first RDD lines. Nothing happens. Then I filter my log files so that I only have errors. Again, nothing happens because no action has been invoked. Then I want to map them because I am only interested in that field, and so that the data set is smaller. Again, no action, no effect. Then I say, now I want to cache, I want to persist this RDD because I'm going to using it quite often. Okay, fine, but you still didn't trigger an action, so I'm not doing anything. And now we start actually checking what's in that data set. We can filter those messages so that we only get the ones that contain, for instance, DNS attack, intruder alert, or this specific user ID is here, and we want to count how many messages match this filter. Count is an action, which means that the moment the interpreter gets this request, my cluster is going to start working. The RDDs will be created, the response will go back to the driver, and it's going to be safe in the cache. Which means that if I run a second instruction on the same cache RDD, this second action is going to execute way faster because I already have kept in memory the actual elements that I had initially here. and I do not need to rerun all those 4 iterations here. So you will see this in the final part of today's lab, but just so that you are not surprised when you see the execution time of one element versus the other. Okay? Well, then let's stop here. Thanks for your time, and I guess this afternoon you will at first struggle a bit with the syntax of Scala. That's normal, but we have provided you the actual snippets, so you can start by copy pasting. And I think once you start seeing how to actually get results back, you will see that it's a quite convenient tool even for data exploration and getting some initial analysis of the system. Thank you.